Allie again. Good to see you guys. Today we're going to be talking about mineral properties and mineral identification. This is Lab 2 of Geology 102. The lab starts on page 2 in your lab manual and goes to page 11 for your mineral properties. I'm going to be walking through the tests and the properties, or the properties and what tests you're going to take to determine those properties today. But what I also want you to do is look at that mineral identification part of the lab. That starts on page 17 and goes to page 31. The last couple of pages are tables that give specific mineral properties along with the mineral identification and their chemical composition. All of that is going to be very important for you guys to look through on your own. I'm not going to walk through each mineral one by one just because that's what the lab is trying to get you to do, it's trying to get you to understand those physical properties of the minerals, and that's what you're going to read about from pages 17 to 31. In-class lab today, it's not today, unfortunately, but throughout the week, what you're going to be doing is filling out this table. It's on page 35 and goes to page 36. You're going to be looking at 12 minerals that I give you in bins, and you're going to be doing different tests on those minerals to determine their physical properties. You're going to write those physical properties down and then use the tables on pages 28 to 31 to identify that mineral. And again, that's why reading about what these minerals are, what their properties are, is going to be very important. So to start, mineral is what rocks are made of, right? So granite, that colorful rock we looked at last week that had red in it, that's made up of minerals. It's made up of quartz, hornblende, plagioclase in its simplest form. Minerals are naturally occurring. They can be formed by organic processes or inorganic processes, but for the most part, they're organic. Minerals have a unique chemical composition and a patterned atomic arrangement that produce distinct physical properties. So to identify what mineral we're going to be looking at today, we need to understand what those physical properties are. A side note, mineraloids are similar to minerals in that they have a unique chemical composition, but they're amorphous. And what that means is that they don't have a patterned atomic arrangement. An example of a mineraloid is opal, so something that's similar to quartz but doesn't quite have that same atomic arrangement in a patterned format. I'll talk about crystals in a little bit. So, physical properties. I wrote down a handful of them here, but there's many more that can be very distinct or very broad in terms. And so these are some of the physical properties that I want you guys getting used to working with today. We have color, luster, streak, hardness, and cleavage or fracture. Some other physical properties that I just want you guys to be aware of are crystal form, a reaction to acid, magnetism, specific gravity, and taste, odor, or feel, and then finally striations. And I'm going to walk through all of these now. So today, what you're going to be doing is you're going to be given a set of minerals, and I want you to determine those physical properties. So to start, the physical property of color. Some minerals can be many different colors. Quartz, for example, can be pink, white, translucent, a darker grayish color, also known as a smoky quartz. So certain minerals can be many different colors, and so that is why, although color is a physical property, we don't want to identify a mineral based on its color alone. I drew the eyeball here just to show that in lab, what you're going to be doing is looking at the minerals to determine the color. Luster is how a mineral reflects light when placed in front of it. So, how a mineral reflects light. Does it look shiny? Does it look dull? Does it look metallic or non-metallic? So something that looks metallic is something that looks like iron or copper. It looks like metal. Non-metallic may look more earthy, dull, brown. An example of a metallic mineral is this right here. It's shiny. It looks like metal. An example of a non-metallic mineral is right here. It looks earthy, right? There's no shine to it no matter how I turn it in the light. Doesn't look like metal at all. Important note, we're looking at new metal, so not rust. Rust would be considered earthy, not metallic. Vitreous, right here, is a glassy luster. So does it look like glass? Does it have that shiny, almost translucent appearance? This would have a vitreous luster. So again, when you're determining luster today, what you're going to be doing is looking at it in hand sample. Is it metallic or non-metallic? That's the first step. Then, if it's non-metallic, describe it a little more. Is it vitreous? Is it dull? Is it earthy? Is it soapy maybe looking? There's many different ways to describe luster, and again, in your lab manual, they walk through many different luster terms that you can use. The biggest thing is that I want you to get used to determining whether a mineral is metallic or non-metallic. Hardness is the resistance to scratching. So what you're going to do in your lab manual is you're going to look at table 1.1. I'm not sure what page it's on, but you can find it in your lab manual. It's within the Chapter 2 Minerals section. What you're going to see is something called Mohs hardness scale. Mohs hardness scale is what we use to determine the hardness of minerals. Again, hardness is a physical property of the mineral. So, hardness is that resistance to scratching. And Mohs hardness scale is what we use to determine that. In lab, we don't have 10 or 12 Mohs hardness scales. And when you're out in the field collecting rock samples and trying to identify them, you're not going to have a Mohs hardness scale in front of you. But for this purpose, I just want to show you what it looks like. It's a group of 10 minerals. There's only 9 here because the 10th mineral is diamond. And it's Oshkosh, we don't have diamonds around here. But it's 10 minerals. One is talc. It's the lowest on the scale. It's the softest mineral. And you'll see this in your lab manual at table 1.1. 1 is the softest and 10 is the hardest. So diamond is the hardest mineral. You can't find anything that's harder than diamond, right? That's why we like them so much and we put them on our fingers. So what you're going to be doing today to compare Mohs hardness scale is you're going to look at that table and you're going to see that some arrows are there that show common materials that can be used in place of Mohs hardness scale. Since I'm not going to be able to hand out Mohs hardness scale to each of you, but I can hand out a few common materials. So what we're going to be working with to determine hardness is a glass plate, a copper penny, and a porcelain plate, also called a streak plate. When you're using these materials today, it's important that you keep the plates flat on the ground. And I wrote that here and started. If you don't keep the plate, the glass, or the porcelain on the ground, if perhaps you did something like this with the mineral, you're gonna break the glass or the porcelain, and it's not gonna be fun. So don't do that. Keep the glass plate flat on the ground, or on the table. And what you're gonna do is you're gonna see in that table 1.1 is that a copper coin has a hardness of 3.3. Glass has a hardness of 5 to 5.5. And the streak plate has a hardness of 6.5 to 7. So what we're gonna do is a few tests using those 3 things. We can also use our fingernail, but I'd like you guys to keep your gloves on in the lab. If you're curious about if your fingernail can scratch a mineral, I can show you after class. I'll just have to I'll have to wash the minerals, that type of thing. But we're gonna keep our gloves on for the lab. So when we're working with Mohs hardness scale, what we want to do is determine the hardness of the mineral based on our 3 materials we have. So the first thing I'm going to do is I'm going to see if this mineral is harder or softer than the penny. Remember, the penny's hardness is 3.5. So this is the one where you can scratch the penny like this. The rest of them, they need to be laid flat on the table. So what I'm going to do is try to scratch the penny on a pointed edge of the mineral. The penny did not scratch the mineral. So what that means is that this mineral is harder than 3.5. It's harder than the penny. Because it's harder than the penny, we don't know anything other than the hardness is greater than 3.5, right? But we want to give a specific hardness. So we're going to move on to the next test. We're going to use the glass plate. I lay it flat on the ground, and I take a pointed edge, and I slowly try to make a groove in the glass. I'm going to brush it off after it because minerals also powder, and we don't want to see the powdery, we want to see if it truly scratched the glass. We can see here that this mineral scratched the glass. What that means is that the mineral is harder than 5 to 5.5 because it scratched the glass. If the mineral didn't scratch the glass, then we would know that it's softer than 5.5. And again, we could make a range between 3.5 and 5.5 would be the hardness of the mineral. But in this case, this mineral did scratch the glass, so it's harder than glass. So now we want to go one more step to determine its true hardness. We're going to use the streak plate. The streak plate has a hardness of 6.5 to 7. I want to make sure my streak plate is clear of debris, so wipe it off. You're going to use your streak plate for other tests as well, so try to use it sparingly. You're going to lay it flat on the table, and again, take a pointed edge and try to scrape it. Just one fluid motion. Don't scrape, scrape, scrape. If you scrape, 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 you're going to powder the mineral, and it's not going to give you an accurate hardness. So one good scrape, and it didn't scratch. It's harder to see on a porcelain plate because it's not translucent, but you can see whether or not it will make an indent in the porcelain plate. So, because it didn't make a scratch in the porcelain plate, that means that this mineral is a little bit harder than the streak plate, so greater than 6.5 or 7. That's the highest hardness we have for common materials. Anything greater than 7, you're going to get into some fancier minerals, but one that is exactly 7 is quartz. So keep that in mind when you're going through your lab. That's all I have to say about hardness. Again, it's really important that you leave that streak plate and that glass plate flat on the table. Now, streak. Here is another physical property of the mineral. Streak is the color of the mineral when you finally powder it. So what I'm going to do is use this mineral here and my streak plate here. Again, the streak plate should be laid flat on the table so that it can't move around and it can't break. What I want to do is scratch the mineral on the plate. Then what I want to do is blow off the excess powder to get the true color of the streak, not of what the powder is. So I can see here, it made a red-brown streak. That is a diagnostic characteristic of one of your minerals. I'm not going to tell you which, but you can read about it in your lab. So that red-brown streak is a physical property of a mineral. That's all I have to say about streak. So now, the last thing is cleavage and fracture. Cleavage and fracture tends to confuse people. It's one of the more difficult physical properties to assess, but we can do it in a few easy steps. Fracture is when a mineral breaks along random irregular surfaces. It has rough breaks in it. This mineral here has rough breaks on it. There's no flat, smooth sides. Everything's rough. And when you look at it in the light, all different angles are reflecting light. Not one side is reflecting light all the way across it. So that means that this mineral has fracture in it. Cleavage is consistent breaks along parallel flat planes. Now I use the word breaks here. You can also use the word cleaves or cleave. And that is where the term cleavage comes from. Minerals cleave off on flat parallel planes known as cleavage planes. So what we're going to do in lab today to determine the cleavage of a mineral is we're going to count the sets of parallel planes with our hands, and then if we were to go another step and determine the angles of cleavage, we would measure the angles using a protractor. We're not going to get into measuring angles today, but it is important to make those distinctive differences in mineral cleavage angles, because certain minerals have distinct angles to their cleavage planes, and that's important. It's important to also note that cleavage planes reflect light. Like I was saying here, this mineral is reflecting light no matter which way I turn it. There is no solid cleavage plane on this mineral. So to describe cleavage, what we want to do is determine the sets of parallel planes. So a good example here is this big piece. This mineral, we're going to count how many sets of parallel planes it has. My bottom hand and my top hand are parallel, right? We can see here, they're never going to cross. Parallel. So that is one set of parallel planes, right? But then we also have a parallel set here and here, right? Parallel. Then finally, our last set is here and here. So that's 3 parallel sets. 1, 2, and 3. That means that this mineral has 3 directions of cleavage. 1, 2, 3. If we were to measure the cleavage angles, we could just use a protractor simply on the corners and measure an angle. We're not going to do cleavage direction angles today. We're just going to count the sets to keep things simple. So again, this mineral has 3 cleavage directions. Another mineral that only has 1 cleavage direction looks something like this. If you look closely, there's many thin layers right on top of each other, but one side is parallel to the other. There isn't another parallel side no matter which way I turn it. So this mineral has 1 direction of cleavage. That's also called basal cleavage. As you go through your lab manual and read through cleavage, you're going to find a lot of different ways to describe cleavage. What I want you to focus on today is counting the directions of cleavage using those parallel sets. So again, parallel set, and parallel set. That makes 3 parallel sets. So that is how you describe cleavage. Next one I'm going to talk about is a few different physical properties that are important but aren't as important for this lab, and they're not as diagnostic for many minerals. They're more specific to 1 or 2 specific minerals. So we also have a hand lens set out for you guys. When you look at minerals, it's nice to get a very clean look at them. What that means is that this hand lens is going to magnify for you. So if you hold up a mineral to the light, you're going to go in and out until you get focused on the mineral looking through the hand lens. You're going to get a lot better view of the mineral up close in person using these hand lenses. So definitely utilize this tool. A few other physical properties of minerals that we can use to describe them and then identify them. One of them is crystal form. I'm not going to go in great detail about crystal form because we aren't going to talk about it in lab much at all, but there is a good page about it in your lab manual. It's page 9. But A crystal is a homogeneous and orderly array of atoms. So what that means is that there's crystals in minerals. Those crystals are homogeneous, so every part of the crystal's composition is the same throughout. And they have an orderly array of atoms. So if I had one crystal and I broke it down to a bunch of little crystals, those little pieces would also be crystals because they still have the same homogeneous composition and an orderly array of atoms. That's something to keep in mind. Crystal form, there's many different forms, and again, those can be described in your lab manual, but for the purposes of this lab, I'm not going to go into too much detail on those. Another physical property that's pretty diagnostic to carbonate minerals is its reaction to acid. Most minerals will not react to acid at all, but carbonate minerals do. Here I wrote reacts to HCl. HCl is hydrochloric acid. We're using a dilute solution of hydrochloric acid in class. They're going to be at everyone's table. It is safe to use. We want to keep our gloves on while we're using it, and we don't want to ingest it in any way. Pretty self-explanatory. If it gets on your clothes, you want to change your shirt and rinse it off. It won't burn, but you shouldn't leave it on your skin for long periods of time at all. So, what I'm going to do for minerals that I think might be carbonate is I'm going to drop 1 drop of acid on it. When I do that, you're going to see that it bubbles. It's bubbling. That means that that mineral is made of carbonate. Its chemical composition is carbonate. After I drop acid on it, I want to dry it off with a piece of paper. You don't want to leave it sit on there because it'll keep eating away at the mineral. And also you don't want to leave it sit on there so that the next person who comes in to touch that mineral doesn't get acid on themselves. So, reaction to acid is one of those diagnostic physical properties that is very specific to only a few minerals. Carbonate minerals, such as calcite, are going to react to acid, and you'll see that in lab. Another physical property is magnetism. You're going to test for magnetism using a small magnet. It's very straightforward. Here's my small magnet. What I'm going to do is go through and touch it to the rock. If it doesn't stick, it's not magnetic. If it does stick, that means it's magnetic. And that's a very diagnostic characteristic of a certain mineral in your lab, and you'll see as you go through it which one that is. Another very diagnostic physical property is striations. Striations are thin parallel grooves that form on plagioclase feldspar. And that's what we use to determine the difference between plagioclase feldspar and potassium feldspar. Again, that word is plagioclase. Plagioclase, or plage, has striations in it, and those are thin parallel grooved lines. There's a picture of it here, and then also I can see it in hand sample here. If I shine it in the light, I see that there's these thin parallel grooves, something that almost looks like a weird knife would have cut it, but it's naturally occurring, and it's specific to plagioclase feldspar. For those of you doing online labs, I highly recommend just typing in striations of plagioclase, because you'll find some very cool images. It's just something neat, in my opinion, that I think people would like to see. Specific gravity is a uniless number that's equal to density. So remember when we talked about density last week, it's a given it's mass in a given volume. So mass divided by volume gives you density. And if you remember, the units on density were grams per cubic centimeter. Specific gravity is very similar to density in that it's a comparison of weights. You're comparing the weight of the mineral to the weight of a specific volume of water. And so when you do that comparison, it becomes a uniless value. But again, specific gravity is pretty much equal to density. So what that means is to compare specific gravities or to compare densities of minerals, you want to get two of similar size. Maybe this one and this one. They're pretty similar in size, right? But when I feel it, this one's heavier than this one. So this one is more dense. That means that this one has a higher specific gravity than this one. A higher density, a higher specific gravity. The two go hand in hand. You're not going to need to test for specific gravity, but it is an important physical property to note because it is easily done by comparing two minerals of similar size and determine which one's more dense than the other. Finally, the last few things that we can do to determine the mineral identification based on physical properties is we can look at taste, odor, or feel. Unfortunately, in this lab, we're not going to let you taste any rocks. We're going through a pandemic right now. We can't do that. But I did give an example of one mineral that is diagnostic based on its physical property of taste, and that is halite. If you guys aren't familiar with halite, this is halite. It has 3 cleavage planes. 1, 2, 3. It's a cube. If I taste it, it tastes like salt. That's because it's rock salt. NaCl. That's its chemical composition. So that is one physical property of halite that makes it diagnostic. To determine the difference between halite and calcite, you could taste them. But remember, we're not going to do that in lab today. We are working with hydrochloric acid and we are in a pandemic, so no tasting minerals. You can also smell minerals. Certain minerals are made up of specific elements that have specific odors. An example is sphalerite. It's a zinc sulfide, so it contains sulfur and it has that rotten egg smell. It's very diagnostic to sphalerite. There is other minerals that contain sulfur, so you need to use a few other diagnostic techniques to determine that sulfur is, or that sphalerite is sphalerite rather than one of those other sulfides. Finally, feel. We are going to have to use gloves in lab, but what you can do is you can feel the difference in certain minerals. So an example of feel is talc. Talc is 1 on the Mohs hardness scale. It's very soft, and when you feel it, it has almost a slippery appearance, kind of soapy-like. So when you're on the field doing your own thing and you want to look at minerals, you can also feel them to determine different diagnostic characteristics of it. That's all I have to say about mineral identification and properties. I'd like you guys to read through that pages 17 to 31 on your own. That's going to talk to you about different rock-forming minerals, different accessory minerals, and a few ore minerals. Rock-forming minerals are the most common minerals we see on Earth today. They're what make up the majority of the rocks on the Earth. Accessory minerals are minerals that are commonly found in rocks, but only in small portions. And finally, ore minerals are minerals that are commonly present in rocks in small amounts, but they're concentrated, so they're mined. So certain minerals have high concentrations of iron in them. That would be considered an ore mineral. So again, page 17 to page 31 has a lot of mineral identification. It's a little lengthy, but it is really important that you guys read through that. Come to class with any questions you have on the minerals, and then what we're going to do is just walk through these 12, and you're going to determine the physical properties and put them into that table. That's all I have. If you guys have any other questions or concerns, please email me. Tutoring also starts this week. It's going to be Monday, Tuesday, Wednesday from 5:30 to 7:30 in room 114 in Harrington, which is next door. We're also going to be doing online tutoring in some format through Collaborate Ultra. You should be getting an email from me, Dr. Hyatt, or Dr. Hallett on that. But if you guys have any questions in the meantime, please feel free to email me. Thanks.